Hello everyone, my name is Zehang. Today I will present our paper Graph-Based Task-Specific Prediction Models for Interactions between Deformable and Rigid Objects. This paper has two contributions. First, we built a novel dataset for task-specific action effect prediction. Different from some previous work, we consider a bag with complex shape and multiple types of interactions. Second, we propose a method for predicting the interaction dynamics based on graph networks. Regarding the dataset, we generate 20 different scenarios by varying different task parameters. For each scenario, we split into 80, 10, and 10% for training, validation, and testing. These are examples of 4 different types of actions. To model the interaction dynamics, we start from what we have in the scene. In the scene, we have a deformable bag and multiple rigid balls. Each ball is represented as a key point, and the bag also has some associated connected key points on the surface. Each key point has a position, a radius, a fixed label flag, and a connection flag with other key points. For the radius here, when it is a ball key point, it is a ball radius. When it is a bag key point, it is a small constant value. The fixed label flag here is either 1 or 0. As shown in the opening case, the key points on the left handle is fixed in place, so the fixed label flag is 1, otherwise it is 0. The C flag here is either 1 or 0. It is 1 only when we assign connections between two key points. We also have some external input. We control one point and move it from one place to another place, which are P start and P end. We also have a radius variable here. When we control and move the ball, it is a ball radius, and when we control and move the back key point, the radius is set as a small constant value. We then convert the observations and the external input together into a fully connected graph. We encode each key point as one graph node, including the position, the radius, and the fixed label flag. The spatial differences and the connection types are encoded as age attributes. The external input are encoded as a global feature vector. Given a graph at time step t, we want to predict the key point position at time step t plus h. Based on the graph representations, we propose a model with 2 different modules for capturing the dynamics, which are called APM and TPM. TPM is used to predict the movement of every key point, and APM is used to predict a binary mask, which indicates if the node is moved or not. In the inference stage, we have different inference models depending on how to use the modules. First, we build a one-stage model by using PPM alone. Then we build a 2-stage model by considering the APM module. APM produces a mask, and we only update the moved particles in the inference. Finally, we propose a mixed horizon strategy for long-term prediction based on 2-stage model. We train 2 different models for short and long horizon. In the inference stage, we combine 2 models to predict the final result. Here's the comparisons of 3 different inference models from vision inspection. The mixed horizon model fixes the sphere's point movement and has more accurate results compared to the original 2-stage model. Here we show one example of comparing the ground truth and our mixed horizon prediction model for pushing action. For quantitative evaluation, we first evaluate the single time step prediction error for the 1-stage and the 2-stage model. From left figure, we see that the 2-stage model decreases the mean position error and also reduces the inter-task variance. From the right figure, the model has similar performance on 2 different materials. We then calculate the long-term accumulation errors for different actions. The 2-stage model always outperforms the 1-stage model. The mixed horizon model reduces the long-term accumulation error, but sometimes produces worse results in short-term prediction. In conclusion, we built a novel dataset and show it is feasible to use graph networks to model interaction dynamics between rigid and deformable objects. The dataset and the code are publicly available. Finally, we would like to thank KAW, PR, ERC, and DFG for the support. Thanks for watching.